So now we can talk about some factoring techniques. In the previous two lessons, we made extensive use of the distributive law. The distributive law is perhaps the most important basic arithmetic process that we can talk about here. So here's the statement of the distributive law: multiplication distributing over addition. And notice that when we start on the left side and move to the right, we say we're distributing P. But of course, this is an equation. We can use it either way. When we start on the right side and move to the left, so we express P now as a factor of the whole thing rather than a factor of each individual term. That is called factoring out. It's very important to recognize that distributing and factoring out are two sides of the same coin. It's the same fundamental process. We just have two different words for it depending on which way we're going in that process. So that's very important to understand. In algebra, factoring is a big topic. Factoring means rewriting any expression as a product of two or more factors. As we will see in the section on algebraic equations, factoring is one powerful equation solving strategy. So this is a very important skill that we will use in solving equations. Before we can employ this strategy in solving equations, we need to understand the various kinds of factoring techniques. So we have a few videos devoted to factoring techniques. This is the easiest of the factoring techniques, simply factoring out a greatest common factor from a binomial. Now, if you haven't seen the idea of a greatest common factor before, I highly recommend going back to the integer properties video where we talk about the idea of greatest common factor with just ordinary integers. This expands the idea to algebra. So for example, if we have the binomial 5x plus 45, just a simple linear binomial, clearly those two numbers have a greatest common factor of 5. So we could factor out a 5 and write this as 5 times x plus 9. Here's another binomial. This one is a cubic binomial. Here we can factor out both a 3 from the coefficients. 3 is the greatest common factor of the coefficients. And also, because we have 3 factors of x in the first term and 1 factor of x in the second term, we can factor out an x. So we factor out 3x, and that leaves us in the first term with 3x squared, and in the second term it leaves us just with 4. So that is a totally factored expression. This expression, very tricky. Probably the powers here are a little bit higher than you're going to see, except on very, very advanced problems on the test. But theoretically, the same principles here. The highest power of x is x to the 5th, so we can factor out an x to the 5th from both terms. The highest power of y is y to the 4th, so we can factor out a y to the 4th from both terms. And that leaves us with x to the 5th times x to the 4th times the quantity x squared plus y squared. X squared plus y squared, those are what's left of the two factors once we factor out x to the 5th and y to the 4th. We could also factor out a greatest common factor from a trinomial. So here's a trinomial. This turns out as a trinomial where the highest power is x to the 4th. And notice that among the coefficients, the greatest common factor is 2, so we can factor out a 2. And the lowest power of x is x squared, so we can factor out an x squared from all the other x's. And so we factor out 2x squared, and that leaves us with just x squared in the first term, just an x in the second term, and simply a 5 in the third term. So we factor this down into 2x squared times a quadratic trinomial. Here are some practice problems. Pause the video here and factor out the greatest common factor. And these are the answers. In this video, we discuss the factoring technique of factoring out a greatest common factor. This lesson discusses perhaps the single most important factoring pattern in all of algebra. We already learned about the square of a sum and the square of a difference. Those two, with this new one, are the big three factoring patterns, and this new one we're learning is clearly the most important. I'll just say, if you're not familiar with the square of the sum and square of a difference, we talked about those in the video on foiling. And so if you haven't seen that video, it may be helpful to watch that video before watching this particular video. This new pattern we're learning is known as the difference of two squares. And as the name says, it's just one square minus another square. So a squared minus b squared, and this factors into a plus b times a minus b. It's easy to see why this is true by using FOIL on the right side. So we just start with a plus b times a minus b, and then simply FOIL out. Well, product of the first terms is a squared. Product of the outer is a times negative b, that would be negative ab. Product of the inner, a times b, that would be ab. And product of the last, b times negative b, would be negative b squared. Now, miraculously, those two cross terms, negative ab and positive ab, those two cancel. And so we're just left with a squared minus b squared. So this is an extremely elegant pattern, and this is precisely why the test is absolutely in love with this pattern. This pattern allows us to factor many different expressions. So for example, starting out just with x squared minus 49. Well, obviously a would be x, because when we square it we get x squared, and b would have to be 7, because when we square 7 we get 49. And so this is going to factor into a plus b times a minus b. That would be x plus 7 times x minus 7. Here's another one, a little trickier because we have a coefficient of the x squared term. 9 is the square of 3. And so 9x squared is 3x times 3x. So a equals 3x, and of course b equals 4, because 4 squared is 16. And so we get 3x minus 4 times 3x plus 4. Incidentally, notice it doesn't matter at all whether we put the binomial with addition or subtraction first. We're multiplying these two, and of course multiplication is commutative. We can switch the order of the factors around, and so it really doesn't make a difference at all. It is mathematically identical whether we put the one with plus first or the one with minus first. So you'll notice in this video I'll just go back and forth switching off between the two because they're both equivalent. 25x squared minus 64y squared. The first one is 5x quantity squared. The second one is 8y quantity squared. So a equals 5x, b equals 8y, and this is 5x plus 8y times 5x minus 8y. Finally, x squared y squared minus 1. X squared y squared, that would mean that a equals x times y, because x times y would be x squared y squared. And of course b would be 1, so this will factor into xy minus 1 times xy plus 1. The material covered by this pattern expands considerably when we realize this: any even power of x is the square of another power. So this is a big idea. First, we can express any even integer as the sum of two of the same integer. So of course, something like 10 would be 5 plus 5, 18 equals 9 plus 9. It's very easy to express any integer as the sum of two of the same integer. And so this is helpful when we think of the sum of powers. Now, if you're not familiar with this sum of powers rule, this is something that we talked about in the multiplying expressions video a few video lessons back. So if you haven't been watching these videos in order, you might have missed that lesson, and that's where we first talked about this exponent rule. And of course, you can learn about all the exponent rules in depth if you skip ahead to the power and roots module. But at the very least, if you've been watching the videos in order, you would have met this exponent rule at this point. And so go back and watch that if it's unfamiliar. But what this means is we could split any even exponent into two powers with equal exponents. So for example, if we had x to the 10th, we can of course write 10 as 5 plus 5, and x to the 5 plus 5, that would be x to the 5th times x to the 5th. So this is the sum of the exponents rule. And of course, x to the 5th times x to the 5th, anything times itself, that is x to the 5th squared. And so this is how we would write an even power as the square of something. I'll also say there's another exponent rule that we haven't talked about yet, but it may be familiar to you. This is the power to a power rule, so this is a little bit of a shortcut. If we have x to the 5th squared, x to the 5th squared means that we multiply the exponents, x to the 5 times 2. And of course we can write 10 as 5 times 2, so that means we can write it as x to the 5th squared. So this is another way to see the pattern. So again, if you're familiar with this rule, you can think about it this way. If you're not familiar with this rule, this is no problem. We will study it in detail in the power and roots module, but you can just think about it the other way, having to do with addition. Either way, the even power of a variable is the square of a power with half the exponent. That's the big idea here. And so, for example, here are a bunch of variables with even exponents, and we can write each one as the square of the variable to half the exponent. So that means that x to the 6th is x cubed squared, x to the 8th is x to the 4th squared, and x to the 12th is x to the 6th squared. Since all even powers are squares, we can use the difference of two squares to factor expressions involving even powers. So let's start out with x to the 6th minus 16. Well, clearly b is 4, because 4 squared is 16. Well, x to the 6th is the square of x to the 3rd. So a would be x to the 3rd. So we would get x to the 3rd minus 4 times x to the 3rd plus 4. That would be the factored form. If we have x to the 8th minus 9y squared, well, x to the 8th is x to the 4 squared. So a would be x to the 4, and of course b would be 3y. So this factors into x to the 4th plus 3y times x to the 4th minus 3y. Okay, this is interesting. We have odd exponents here. But notice the following. Notice we can factor out a greatest common factor. We talked about this a couple videos ago. Factoring out a greatest common factor, we factor out an x to the 5th, then we're left with x squared minus 4. So we've already written this as a product, but we can factor even further. We can factor that x squared minus 4 using the difference of two square patterns, and that is the fully factored form of that original binomial. Here's another one. So of course we can factor this. X to the 4th is x squared squared. So a equals x squared, b equals 9. We can factor this into x squared plus 9 times x squared minus 9. But notice that x squared minus 9 is another difference of squares. So we can factor that one again and factor this. So we have x squared plus 9 and times x minus 3 times x plus 3. And that is the fully factored form. So any difference of squares we can factor further. Notice that x squared plus 9, that's a sum of squares, and there's actually no way to factor that. It's worth noting that there's no way at all in algebra to factor the sum of two squares. The big three patterns to know are the square of a sum, a plus b squared equals a squared plus 2ab plus b squared. The square of a difference, a minus b squared is a squared minus 2ab plus b squared. And then the really important one, the difference of two squares, a plus b times a minus b, is a squared minus b squared. So here's some practice problems. Pause the video and factor these fully, and then we'll talk about them. First one is very easy to factor. Second one, we can factor this. The third one, we factor out an x, and then we factor out into x to the fourth plus 1, x to the fourth minus 1, but that's the difference of squares, that second one, so we can factor that further. And then that x squared minus 1 is another difference of squares, so we can factor that further. So it turns out we get 5 different factors. That is the fully factored form of that last expression. Here's a practice problem that's a little more test-like. Of course, there are only 4 choices instead of 5 choices, but this is a multiple choice test in the feel of what you might see on the real test. So pause the video, and then we'll talk about this. Okay, so let's think about this. Let's start out with these first 2 equations, y equals 5 plus x and y equals 12 minus x. We rewrite a little bit. We see what we're given here is what y minus x equals and what y plus x equals. So that's interesting. Hold on to that for a moment. Then we want to know what k equals. Well, clearly k equals y squared minus x squared. Well, we know we can factor y squared minus x squared into y minus x times y plus x. And we know those 2 values. We know y minus x is 5 and y plus x is 12. So this is just 5 times 12, which is 60. So k equals 60. In this lesson, we discussed the difference of 2 squares pattern and how to use it in factoring algebraic expressions. The most challenging topic in factoring is knowing how to factor a quadratic trinomial into the product of 2 linear binomials. So for example, here's a quadratic trinomial, 3 terms, highest power is x squared, and we want to factor this into 2 linear binomials. Each one, of course, has just a highest power of x. That is the factored form. For example, on the test, we might have to factor something like x squared plus 4x minus 21. Now, I'll point out, this is probably not going to be an entire test problem. Yes, there may be an entire test problem that says, here's a quadratic, factor it, but more likely, factoring the quadratic is a skill that you're going to need in solving a much larger question. But this is definitely a skill you will need. Let's think about the details of the FOIL process. Understanding factoring really comes down to understanding the mechanics of foiling. Suppose we start with 2 generic linear binomials, x plus p and x plus q. So we'll FOIL these out. Of course, product of the first is x squared, product of the outer qx, product of the inner px, and product of the last pq. Now notice pq, that's 2 numbers, so that's the constant term. X squared is the quadratic term, and the 2 middle terms are linear terms, and they are like terms, so we can combine the like terms, and we get this. Now this is very interesting. Imagine we look at our quadratic trinomial, and we see this. So really, that linear coefficient is p plus q, and that constant term is p times q. So in other words, the linear coefficient of the quadratic is the sum of the 2 unknowns we're looking for, and the constant term of the quadratic is the product of the 2 unknowns. Very interesting. Let's apply this in a problem. Suppose we have to factor this. So in other words, we're looking for 2 numbers whose sum is 8 and whose product is 15. Well, there aren't many numbers we can multiply together to get 15. We could do 1 times 15, that doesn't have the right sum, or we could do 3 times 5. 3 and 5 are clearly the numbers, and that means we can factor this into x plus 3 and x plus 5. That is the factored form. Notice here we have a statement that is true for every number on the number line. That's why we can set an equal sign between these 2 expressions. We'll factor this one. We need a pair, they have a sum of 14 and a product of 24. A little bit trickier because there are many factor pairs that multiply to 24. We could do 4 times 6, that's not the right sum. We could do 3 times 8, that's not the right sum. We could do 2 times 12, that's the right sum. And so the numbers that we need are 2 and 12, and this is the factored form, x plus 2 and x plus 12. This one's a little trickier. We have a negative sign. So here we're looking for a sum of positive 4 and a product of negative 21. Let's think about this. Since the product is negative, one of the two numbers must be positive and one is negative. Since the sum is positive, it means we're adding these two numbers and getting a positive. That means the larger number, the number with the larger absolute value, must be positive. So we'll think about this. First of all, think about factors of 21. Certainly 3 and 7 multiply to positive 21. So let's make the larger of those two a positive number and the smaller of those two a negative number. If we have positive 7 and negative 3, those multiply to negative 21 and they add to positive 4. So those are the two numbers that we're looking for, positive 7 and negative 3. And so that means that we can factor this into x plus 7 times x minus 3. And for all of these, incidentally, as you're practicing factoring, I would suggest once you think you have the factored form, a very good way to practice is FOIL those two on the right and make sure you wind up back at the form on the left. In other words, if you can factor one way and then FOIL back to what you got, you really understand this very well. Here's another one. Here we need a sum of negative 2 and a product of negative 35. So we know that one is negative and one is positive of the two numbers we're looking for because they have a negative product. And the one with a bigger absolute value is negative. So what can we multiply to get 35, first of all? Well, one obvious choice is 5 times 7. So let's make the one with the bigger absolute value negative. So we'll have positive 5 and negative 7. They multiply to negative 35 and they add to negative 2. So these are the numbers that we need, and we can factor it into x minus 7 and x plus 5. Now this one's interesting. Here we have a positive product but a negative sum. Well, how does that happen? Well, this means that both the numbers are negative. Because in other words, if you have negative times negative, that will give you a positive, but if you have negative plus negative, that will give you a negative. So both numbers must be negative. So we need two numbers that multiply to 48. And really one way to think about it is they multiply to 48 and have a sum of positive 16, and then we'll just make them both negative. Well, certainly 6 times 8. 6 times 8 has a sum of, 6 and 8 have a sum of 14. That doesn't work. We could do 4 times 12. 4 times 12 has a sum of 16. So negative 4 times negative 12 would be positive 48, but negative 4 plus negative 12 would have a sum of negative 16. These are the two numbers that we need, so we can factor this into x minus 12 and x minus 4. Incidentally, notice once again with multiplication, it doesn't matter the order that we write things in. I could have written this as x minus 4 times x minus 12. Same thing. Doesn't matter at all because multiplication is commutative. We can write the factors in any order. Here are some practice problems. Pause the video and factor all of these. And here are the answers. Notice that this method only works if the coefficient of x squared, the quadratic coefficient, is 1. If the quadratic coefficient is something other than 1, chances are very good that one of the other factoring methods can be used. Say the difference of two squares or a greatest common factor. It may mean that we have to factor out a greatest common factor, and then we get an ordinary quadratic. So we'll have to talk about combined factoring techniques if something like that comes into play. And that's what we'll talk about in our next video. In this lesson, we learned the method for factoring a basic quadratic into a product of two linear binomials. The linear coefficient of the quadratic is the sum of the two unknown numbers, and the constant term of the quadratic is the product of the two unknown numbers. Now that we have learned a few different factoring techniques, sort of like a bag of tricks we can explore methods for combining them to factor more challenging expressions. These combined techniques would be applicable only on the most difficult quant problems on the test. So what I'm covering in this video is relatively advanced. For example, suppose you had to factor something of this form. Well, notice, first of all, we can use our old trick of factoring out a greatest common factor. And of course, the greatest common factor, both coefficients are divisible by 6, and we can factor out an x as well. So we factor out a 6x, and we get x squared minus 25. Well, and of course, now that's a difference of 2 squares. So it factors to this, and this is the fully factored form. Suppose we had to factor something like this. So this isn't too hard. This could appear many places on the test, something of this form. So notice, first of all the coefficients are even, so we can factor out a 2. Once we factor out a 2, then we get an ordinary quadratic. Now it's just a matter of factoring that ordinary quadratic. We need a product of 24, a sum of negative 11. So those two terms are negative 3 and negative 8. And so this factors to 2 times x minus 8 times x minus 3. This one's a little bit trickier, and that's certainly a scary looking trinomial. But notice that, first of all, every coefficient is divisible by 7, so we can factor out a greatest common factor of 7. And also, we can factor out an x squared. So if we factor out 7x squared, then we get x squared minus 8x minus 9. So that now, again, is an ordinary quadratic. We need a product of negative 9 and a sum of negative 8. So plus 1 and negative 9 would be the two numbers that would satisfy that. And so this can be factored into 7x squared times x minus 9 times x plus 1. Another scary looking thing. Well, first of all, we can swap the order around so that we have a positive first and a negative second. That makes things a little bit easier. We can factor out a factor of 3, and we can also factor out a single factor of x. That's the greatest common factor. And that gets us down to 3x times the quantity 16y to the 4th minus x to the 8th. Well, those are both even powers, so they're both squares, and of course 16 is a square. So 16y to the 4th would be the square of 4y squared, and x to the 8 would be the square of x to the 4th. So we can factor this into this. Now notice that that last parenthesis, 4y squared minus x to the 4th, that is another difference of squares. So we can factor that by the difference of squares again. 4x squared is the square of 4y squared is the square of 2y, and x to the 4th is the square of x squared. And so altogether, this factors to that. Now this would be a very, very advanced problem that would only appear on the hardest part of the test. I'll also say the factoring these problems is about as hard as any factoring you'll need to do on the test. Keep in mind though, the test will rarely hand you something as straightforward as factor this. Here's some ugly algebraic expression, factor it. That doesn't often happen. Factoring is unlikely to be the thrust of an entire problem, but you will need to factor as a step in a larger complicated problem. So having these skills of factoring, even factoring these really hairy expressions, is something that can help you unlock those harder quant problems. We will see some examples of factoring used in equation solving in the section on algebra equations, at the end of our section on algebra expressions. In this lesson, we talked about combining the individual factoring techniques to factor more complicated expressions. So now we're going to take a break from algebra and go back to just pure numbers. Now remember, we will return to the idea of prime factorizations from the interproperties module. Now, if you haven't seen that module, I would highly recommend watching that lesson on prime factorization so you appreciate how important it is to find the prime factorization of a number. Once we have the prime factorization, we can find all the other factors, we can find the number of factors, we can do any one of a number of things if we have the prime factorization of a number. Well, it turns out, now that we have learned these algebraic factoring techniques, and especially the difference of two squares, we can use some of these to factor numbers that otherwise would be very hard to factor. So, for example, suppose you had to find the prime factorization of 1599. Well, that would be hard. We could probably tell from our divisibility tricks that since the sum of these is, let's see, 24, then that's divisible by 3, so the number would be divisible by 3. But even if we divide this by 3, then we're going to get some ugly 3-digit number that's not going to be easy to factor. Well, it turns out there's a much easier way, a very elegant way to get to the prime factorization. Simply notice 1599 is 1600 minus 1. That's a difference of squares, because of course 1 squared is 1, and 40 squared is 1600. So what we have here is 40 squared minus 1 squared. Well, following the difference of two squares pattern, this is 40 plus 1 times 40 minus 1, or in other words, 41 times 39. 41 is a prime number, but 39 we can factor into 3 times 13, and these are the three prime factors. That's the prime factorization of the number. So a very elegant way to get to the prime factorization of the number. Suppose we had to find the prime factorization of 2491. I'm going to tell you at the outset this would be a very hard number to factor. Even if you had a handheld calculator in your hand, it would be hard to find the prime factorization of this number. Well, what can we do? Well, notice this one also is 2500 minus 9. 2500 is 50 squared, and of course 9 is 3 squared. So this is 50 squared minus 3 squared, a difference of squares. We can write this as 50 minus 3 times 50 plus 3, 47 times 53. That is the prime factorization. Those are two prime numbers right there. And again, that would be incredibly hard to find even if you had a handheld calculator at your disposal. But here, we can find it directly and elegantly using the difference of squares. Suppose we had to find the prime factorization of 9975. Well, looks like it would be divisible by 25, but then we'd get some other ugly number that we had to divide. That would be difficult doing it the conventional way. But notice that this is 10,000 minus 25. 10,000 is 100 squared. And of course 25 is 5 squared. So this is 100 squared minus 5 squared. 100 plus 5 times 100 minus 5. That gets us down to 105 times 95. And we can factor each one of those. 105 is 5 times 21, and 95 is 5 times 19. 21 we can factor into 3 times 7, and here's the complete prime factorization. 5 squared times 3 times 7 times 19. So in an instant, we get the prime factorization simply by making use of the difference of two squares formula. If there is a large 4-digit number on the test, and to solve the problem you realize that you would need to have the prime factorization of the number, it is very likely that the test is expecting you to recognize that that large number can be expressed as the difference of two squares. This technique can also help with factoring many large numbers, and it can help with decimals. Decimals. Let's think about this. Consider this decimal. Suppose for some reason we needed to find two numbers that we could multiply together to get that decimal. Well, doesn't sound like a very fun thing to do, but notice 0.9991 is 1 minus 0.0009. And that's a difference of squares because 0.0009 is 0.03 squared. So we can write this as a difference of squares, use the pattern 1 plus 0.03 times 1 minus 0.03. This gives us 1.03 times 0.97. And so we have expressed that decimal as a product of two decimals. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so clearly we're going to write both of these as 1 minus something. The top is 1 minus 0.000049. The bottom is 1 minus 0.007. And notice that that top decimal, 0.000049, is 0.007 squared. And so this means we can write the top in the difference of two squares pattern. We get a 1 plus 0.007 and a 1 minus 0.007. That second factor, the subtraction, appears in the denominator, so we can cancel it. We're left with 1 plus 007, and we get 1.007. And that is the quotient. And we get that very easily using the difference of squares pattern. Here's another practice problem. Pause the video, and then we'll talk about this. Okay, in that fraction, we're going to write each one as 1 minus something. 1 minus 0.000144, and in the denominator, 1 minus 0.012. Well, 0.012 squared is 0.00014. So on the top, we have a difference of squares. We'll cut directly to the difference of squares pattern. We'll cancel the subtraction, and then now we just have addition, and we can do the 1 minus 1. They cancel, and we're left with 0.012. And so that entire ugly fraction at the beginning simplifies to this lovely little decimal. Remember that the difference of two squares pattern can be powerful in finding the prime factorization of large numbers or in simplifying decimals just less than 1. In this lesson, we will examine rational expressions. Now, what exactly are rational expressions? A rational expression is a ratio, a fraction of two algebraic expressions. So, for example, x minus 3 over x plus 2, that would be a rational expression. Many of the rational expressions you will see on the test will be ones that can be simplified, and your job will be to simplify them. To simplify a rational expression, we have to factor the expressions in the numerator and the denominator, and then cancel the common factors. So, for example, suppose we're asked to simplify this rational expression. Well, we have an ordinary quadratic in the numerator and another ordinary quadratic in the denominator. In fact, the one in the denominator is just the square of a difference pattern. So when we factor, what we get is x minus 3 times x plus 7 in the numerator, x minus 3 squared in the denominator. We can cancel a factor of x minus 3, and we're left with x plus 7 over x minus 3. And that is a simplified form of the same expression. Here's another one. The expression on the top is a bit tricky, but notice that we can factor out a greatest common factor, and then that just becomes a difference of two squares. The denominator is just an ordinary quadratic, so we factor that in the ordinary way. We have an extra factor of x plus 2 that we can cancel, and this simplifies to 2x squared times x minus 2 divided by x minus 7. Now this is tricky. We have a y squared plus 2x minus 8 over x minus 4. Well, this one, we can't do any factoring because we have two different variables in the numerator, but here's something else we can do. We can always split a fraction up by addition or subtraction in the numerator. So we can split this up into two fractions. It's sort of the opposite of finding the common denominator. We split them up into fractions with a common denominator. So we get a y squared over x minus 4, and we get a 2x minus 8 over x minus 4. Well, notice in that second fraction, we can factor out a 2 in the numerator, and we get 2 times x minus 4. Well, the x minus 4 and the x minus 4 cancel. So the first fraction, we can't do anything with that. We can't simplify it at all, but the second part just becomes plus 2. So sometimes it's very useful to separate a fraction out by addition or subtraction in the numerator, and then simplify one piece of it. Here's a practice question. Pause the video and work on this. So, okay, if we're going to do this a very straightforward way, we might cross multiply. We get 22 times x plus 15. I don't want to have to figure out what 22 times 15 is. Then we'd have some very large quadratic that we'd have to solve. Well, notice the following. Notice if we start with this and just factor the numerator of that. We get a factor of x plus 15. Cancel those x plus 15s, and we're down to the equation 22 equals x minus 3. So x, of course, equals 25. Notice how deviously easy this question is if you realize you can simplify by canceling. Here's another practice question. Pause the video and work with this, and then we'll talk about it. Okay. So obviously we can't factor here because we have a bunch of different variables. But let's start with that. And I'm going to say, let's group them a little bit differently. Let's put the 3q in front, and let's get the p and the r together. And then we'll separate out. So we have the numerator without p and r separate from the numerator with p and r. So it looks like that first one we're not going to be able to factor at all. But that second piece, we can factor out a 4 in the numerator, then cancel p minus r. And what we're left with is 3q over p minus r plus 4. And this equals the original expression. Well, that's interesting. The original expression equals 19. So if we subtract 4 from both sides now, we get 3q over p minus r equals 15. Well, now we'll just divide both sides by 3, divide that numerator and divide the other side by 3, and we get q over p minus r equals 5. And thus we have answered the question. In this lesson, we learned how to simplify rational expressions by factoring the numerator denominator and canceling the common factors. We also learned how to simplify by separating the numerator into two parts.